All right. So this is the last part of the chapter 3. And first question is asking us to find percentile. And to do that, the first thing you wanted to do is order a number from high to low. Right? So I'll go with 23, 27, 29, 30, 31, 33, 38, 40, 42, 43, 51. Right? So we have this set of data, and there are 11. Samples there. So the question asks us to find the percentile for number 33 or client 33. So percentile from what we talked is number of values below x, right? X is 33, right? So this is the x I'm interested in. Anything below that guy divided by the total number or the total number of clients I have. So total number times 100%. Now, if I do this, I have 5 individuals in front of 33 and total of 11 times 100, which gives me 45%. So this is what it says is anything below this guy is within those days, she has seen 45% of her clients in the first 5 days. Now, if you look at it without doing this calculation, halfway through, or this should be halfway through the data, right? Because it's equally split. So the problem with this equation or this formula is, which it doesn't include in our book, is number of values below x plus 0.5, right? Divided by total number of value times 100. So this should give you exact answer. Our book doesn't include it for a reason that I don't know. So we'll stick with this, and this is also work. So some books use that 0.5 to offset the difference. Okay. If I do with this, it will be 50% higher. Some books use this, some books use this. So that 0.5 to 5% change. So let's do number 2. We need to find quartiles, right? Quartiles is also part of percentile, so therefore it goes increment of 25. So Q1 is anything below the median, which is, in this case, was 33, right? Clear? Halfway through, equal amounts, both sides. So Q2, or the median, is 33. And anything below, halfway through, will be Q1, 29. Is that clear? And Q3, without including what? Q2, all the way here, halfway through, which is 42. Right? So we use this information to plot box plot. To do box plot, you need 5 numbers. And the minimum with maximum somewhere here with Q1, Q2, Q3. The minimum for this is 23. The maximum is 51 client, and Q1 is 29, 33, 42. So one thing about doing a box plot, right? If you just put a box around and say this is 23 and this is 51, and you have Q2 here, Q3 here, Q1 here, doesn't say a lot about the scale here. So you wanted to put that as scale. So if I start with a scale of 20, and I'll go increment of 5, right, if I go increment of 5, now I know that my minimum is 23, somewhere right here. With Q1 is 29, right there. With Q3 is, Q2 is 33, somewhere along here. Q3 is 42. And maximum is 51. So I'm right. So my box goes into the only the quartiles, and the whisker goes for the minimum and the maximum. So this is minimum, Q1, Q2, Q3 with a max. Any question? Any question? Okay. So as percentile, quartiles, and box plot. Last week we started on probability, and we got to somewhat a little bit explain about what large number is, and I will start from there. Before I start from there, what I wanted to do is I want to do a few things. The first thing I wanted to do is let's just talk about one coin, and then hopefully bring those the first part of chapter 4 that we did last week, and hopefully that will help you to get on track. I have a coin, right? How many outcomes can I have out of this coin? 2, right? I can have only 2. So if I have one coin, I can have 2 outcomes, right? One is, right? Assuming the floor is flat and just landed either side. Okay? That's the assumption we have. If I have a dice right here, for the sake, how many outcomes can I have from this dice? 6 sides, right? I have 6 sides, so that's a possibility of 6. So if I have one dice, I can have 1, right? 2, 3, 4, 5, and 6. Right? Clear? So when we talk about probability of some event, right? What do we say? What is probability? Let's define what probability is. Last class. We did this in last class. What is the formula?
1 of 6.
Well, let's subvoid this. Let's subvoid and let's go back to the equation. What is the formula for probability?
The number of outcomes and
The number of outcomes, some event, right? Outcomes on some event divided by what?
the number of outcomes
In sample space.
Yeah.
Right? Number of outcomes in sample space. Sample space. Okay? So this is theoretical probability where every event have equal chance being selected. Is that clear? So every chance has equal chance being selected. So if I have a coin, right? What is my probability getting either tail or head?
1 over 2.
1 over 2, right? That's my probability getting either tail or head. It's theoretical value. It's already determined that the outcome will be 1 over 2, right? When we talk about sample space, which we'll get to it, is this is your sample space. The possible outcome in your event. So if I'm tossing one coin, I will have a sample space of either tail or head. Okay? Sample space is the possible outcome in your experiment. Right? Here, if I throw a dice, I have a possible outcome of 6 events, right? So this is called a sample space. Now, let's go back to determine what the probability of getting tail. Right? So the number of outcome in event coin, they just call some event coin. So if I toss a coin in, what's the probability of getting tail? Okay, in one coin, how many tails do I have here?
1.
Only one tail, right? So the only tail I can get is one tail. Out of how many sample space? 2, right? So that's how you determine that 50% or 1 over 2. Okay? So let's just do one more here. If I toss a dice on my experiment, right, I will have a sample space of 1 through 6. Like 6 events, possible outcomes. Okay? I can't have anything more or less. Right? So if I'm interested to find the probability of getting 4, right? How many 4s do I have in my sample space? It's only 1, right? And it says the total outcome of in your sample space. This is my sample space. How many do I have here? 6 possible outcomes, right? But out of that, 1 is 4. So the probability of getting 4 is 1 over 6. Okay? Now let's extend this a little bit more, and we'll get to it, hopefully it will make sense. So if we already said that, if I'm tossing a coin or a dice, we just do a dice, right? If I toss a dice, in my sample space I have 1, 2, 3, 4, 5, and 6, right? And we said the probability of anything in it was in that dice, right? What is the probability of getting 1? 1 over 6. What is the probability of getting 2? 1 over 6. All the way down to the last value you have will be 1 over 6. Now some of you will say, okay, this doesn't make any sense. If I choose this, I will have 1, which is 1 out of the 6 event that can happen. If I choose another one, I have 4, right? Only 1 4 out of the 6 space I have here, right? The same for the coin. If I toss a coin, either getting head or tail is 50%, right? Is that true?
Yeah.
So within my sample space, each of them will have a probability of 1 over 6. So this is determined theoretically by that equation. Okay? Just keep this in mind. This is your sample space. Sample space is the possible outcomes in your experiment. Any experiment you do, it can be a true-false question. Let's do questionnaires, right? If I have here question, and it's only true-false, right? So that's the only possible outcomes I'll have, true-false. And each of them have 50-50%, right? If I'm playing soccer, assuming that you can have win, you can have loss, or you can have tie, right? So my possible outcome playing soccer with another team will be I win, or I lose, or we both tie. Right? Clear? So sample space contains the possible outcomes of that experiment, or any experiment that you perform. Okay. Now, if this soccer game doesn't have an option to be a tie, right, then one has to win or has to lose, right? Then by then the probability goes up to 50%, right? Right now is what, 33% each, right? So that kind of thing you have to play around with what really happening or what situation that you have to use. But knowing that sample space contains the possible outcomes of your experiment. Okay? Now, we talked about law of large number last week. We talked about law of large number. We said that if I'm tossing a coin, and let's say I toss this coin 10 times, I can have a possible outcome of 5 head or 5 tail, right? Or I can have all of them tail, 10 of them tail, or I can have 0 head, right? Vice versa, right? The combination can be all sort of. So what the law of large number says is that if you increase your experiment sample, right? If I'm increasing this from 10 to 100, 100 to 1,000, 1,000 to 10,000, increase this number, I should approach to my theoretical value of 1 over 2 for the coin, either tail or head, right? If I'm increasing the experiment sample that I'm doing, right? If I do 10, all of them can be either 5 heads or 5 tail, right? Or it can be 10 tail and 0 head, right? But if I'm increasing this samples to really, really, really large number, that should approach to the theoretical value that was determined to be 1 over 2, either for tail or either for head. Okay? So the law of large number, especially for probability, just pretty much says that if you increase your sample space or sample experiment to a very large number, it should approach the theoretical value that was determined to be for that event. In this case, coin is 1/2. For a dice, you will have 1/6. If I'm only interested in looking into, let's say 2, right? Keep throwing, and keep throwing, and have a very large sample experiment, that 2 should approach to 1/6. Okay? So that's the law of large number. Now, we said that having, if I have a dice, we kind of went over this, if I have a dice, then 1 through 6 is your sample space. Sample space contains the possible outcomes you have in your experiment, any experiment you do. Okay? The same for a coin. You have one coin, you toss on one coin, you can have either tail or head. Now, if I increase my number of coins that I'm performing or I'm experimenting, then the probability goes down, right? Right? We'll do that. Events, right? This is an event, tossing a coin, right? Soccer can be event that I'm looking into, or having a dice or a questionnaire that is true or false is an event that has a possible outcomes of a problem that determined to be theoretical value. Now, there's a few rules. The sum of the probability within all of you in your sample space has to equal to 1. What it's supposed to? Let me explain this because this is very fundamental. This is my sample space for a dice, right? I have possible 6 outcomes. I don't know what that will be if I toss this, but I know that for sure I have 6 possible outcomes. What this tell you, the last point is, if you sum the probability, the sum of all the probability within your sample space, it should add up to 1. Okay, that's a mess. So if I add 1/6 plus 1/6 for each event, my sample space, okay, I'm just dealing with sample space. Within my sample space, the sum of the probability has to add up to 1. Okay, so if I add this all the way down to 1/6, I should have 1, 2, 3, 4, 5. I should have 6/6, right? So that is rule number 1 that need to be very careful when you do probability. Especially, this is determined. You know the probability of getting 1 or 2 is 1/6, or getting either head or a tail for a coin will be 1/2, which is 1, right? This is already determined values, theoretical value. But when you're dealing with something that's not theoretical, you need to be very careful that the sum of all of your probability in sample space has to add up to 1. It's 1 number. The other one is, if it's not here, if the probability of something approaching 1 or is getting close to 1, that means that that event is happening. That's the possibility of that event happening is very high. Okay. I'll go back to this slide right here. Okay. So if I toss a coin, I have equal chance, 50-50, right? But I know that most likely this winter or this coming winter we'll have a snow, right? I'm not 100% guaranteed that it will happen, but from previous experience that this will approach close to 1. The probability of we getting the snow this coming month will be higher here, right? It's approaching to close to 1. That means that event is happening. If the probability is approaching to 0, or at least getting close to 0, right? That doesn't mean that it won't happen. That doesn't mean that you will not win a lottery, but the chance that you win in Mega Million is very slim, very small. Okay? So it's getting to the impossible point. Okay? So the sum of all of your probability within your sample space of that experiment has to equal to 1. Right? If something is approaching, the probability approaching close to 1 is that that event will occur or happen. And if it's approaching to 0, the possibility of that event happening is very less. Okay? Is that clear? Now, within probability. And there's another rule called complement of any event. In this case, event A. Okay, that's event A. And when we talk about complement, our book use this symbol, A to the power of C. Okay. It's called complement of event A. Okay. The complement of that event A. In this case, if we're tossing a dice, the complement of tossing a dice. If you're tossing a coin, complement of tossing a coin. Okay. That A is just a symbol of any event. Okay. Some books use this. A bar. The same thing. If you come across some notation that used in this book, but not some other book that you're using, A complement, the same thing. Okay, let me get that out from my way. Now, when we talk about complement, I'll take the equation. The probability of any event A plus the probability of its complement has to equal to 1. Now, the sum of all probability in your sample space has to equal to 1, right? So the sum of all the probability in your sample space, which is in this case dice, has to equal to 1. That is rule. We cannot forget about this. Now, if this is true, what this says is the probability of the event A plus its complement has to equal to 1. Before I give you the definition, I have one coin that I'm tossing, either head or tail possibility. Okay? If I'm only interested in looking into the probability of getting head, the complement will be tail. So when we talk about complement, it means that within the same sample space that you have, if you're looking for one event within that sample space, the complement is the event that doesn't occur. Right? So if I'm only looking between one point, if I'm only interested looking into head or tail, and in this case I'm interested looking into head, the complement will be tail. Okay? The event that doesn't occur within the same sample space. Okay? If I go back to dice, if the probability is getting 4, right? Probability of getting 4 would be 1/6. The complement would be not getting 4, which is the rest of the numbers. So we talk about complement within the same sample space, has to be within the same sample space. Okay, that's one requirement. And then the second one would be, if you're only looking into one of the outcomes within your sample space, the complement will be the event that doesn't occur within the same sample space.
So would it be 5/6?
Yes.
Yeah.
Yes. Okay. So what she said is, if I'm only looking for the probability of 4, which is 1/6, the complement will be not getting 1, 2, 3, 5, and 6. Right? And 6. That would be my complement. Because I'm only interested in looking into what the probability of getting 4 will be, which is 1/6. Then the complement will be the event within the same sample space, because we define that to be a sample space, the possible outcomes, right, for your experiment. In this case, it's dice, so I have 6 possible outcomes. So if I'm only looking for to get the probability of 4, the complement will be the event that doesn't occur. That will be 1, 2, 3, 5, and 6. Which will be 5/6. Right? Because this rule has to be met. The complement of that experiment, which is a dice, plus the probability of that event has to equal to 1. So therefore, the probability of getting 4 is 1/6. The complement has to be 5/6, which will give you this rule to be true. Okay. Any question for complement? Complement of any event, go ahead.
So it's just a check, like at the end of figuring out our formula. This is a good way to check like if we have the numbers correct and.
Well, you should check this by this rule. The probability of all of your outcomes within your sample space has to equal to 1.
Yeah, and that's what it's used for, is to just check to see if you have.
That is 1.
That information.
This rule says if some event doesn't occur within your sample space, that will be the complement of the event that will occur.
And then what if there's 3 different, you go saying can there be more than 2?
More than what? So
Or more than one complement?
within the same experiment? No.
No?
Well, if you think about it, this event to be more than 1, yes.
No, I just, I was just adding that like if you threw a third variable in there.
No, because it has to be within one sample space. This experiment is in one sample space.
So what if you're looking for 2 and 3? It would just switch. You just put 2
Sure,
and 3
yeah.
together.
So the probability of getting 2 or 3, and then the complement will be not getting the rest of the,
Yeah, so
exactly.
2 over 6 and 4 over 6.
Yes.
Together you do 6 over 6.
Yeah. Yeah, you can have that situation, but within the same sample space, within that one sample space. So the example I have here is if the event that you're looking for is Monday and Wednesday, the complement will be not getting Monday and Wednesday. Therefore, you will have Tuesday, Thursday, Friday, Saturday, and Sunday. Okay. The event that you're interested in on Monday and Tuesday, Monday and Wednesday, then the complement will be not getting those days, which is the rest of the week. Okay. So complement is within the same sample space. That if some event that you're interested in the same sample space, the complement will be the event that doesn't occur. That has to be within the same sample space because that has to equal to 1. Should we do some practice? One. Yeah, let's do some practice. First 9 questions.
No, we should do it. Oh, we're doing that.
Alright, the first question. For recent year, there were, so number 1, 6,511,100 car crash among among 135,670,000 registered registered car. So the question says that within a year or within 1 year, there is 135 million registered car in this country. And that year, there was 6.5 million car accidents, okay, among the registered car. So the question is, find the probability that randomly selected car out of this. Okay? If I select randomly out of this population, what is the probability of getting a car accident? Okay, go ahead. No, an email. I don't have it. So the probability of crash. I'm sorry.
I was just letting you know I was looking at with him already.
Can you read that number again? I can't.
6,511,100 car crash, and this is 135,670,000 registered car. Okay.
The last three is zeros?
Yes, the last actually 4 is zeros. Yes. So this is my population, right? If you go back to chapter 3 and 2, that I have this is the number of cars registered within that population. Out of this population, there is sample of car accidents that I have, which is the 6.5 million, approximately, and I'll call this 136 million. Okay. So within that registered car of my population of 136. There is 6.5 million car crash occur within 1 year. So we wanted to find out what's the probability of getting a crash any given year. Okay. So the probability of getting a crash is, if I know my sample is 6.5 over the total of the frequency in this case, because we can use this. Why can we use this? I'm using this equation, which is relative frequency. Why can I use this?
Because it's only one.
It is only one.
You only compare one car crash, for that year or something, or
Okay, you're going somewhere in that direction.
because that sample is higher, bigger compared to the first one?
Okay, so we don't have equal amount of car crash or no crash, right? We don't have equal. So if I toss a coin, there is 50% chance me getting either tail or head, right? But on my car crash or this experiment here, they don't occur at the same amount. Okay, so therefore I can't use this equation. What I can use is the relative frequency probability, where the frequency of that occurrence, in this case 6.5 million, divided by the sum of all the frequencies, in this case the sum of all registered cars. Because this has to be, all the events within this experiment have equal chance or equal likelihood of having the same amount. Okay? So I can use this for a crash, because the number of car crash and the number of not having car crash not equal. Does that make sense? The number of car crash I can have and the number of not having a car crash not equal for this experiment. Okay? Because in this event, or theoretical probability, the event of any experiment that you do have equal chance or equal likelihood of being selected. Okay? This guy, we don't have the same amount of car crash with the amount of car registered. Okay? So the only thing I can do is I'll use the probability of having a crash is the frequency of that sample divided by the number of cars registered within that population. Okay, so in this case it's 136 or 135,670. Okay. Crash over total registered car. So the number of crash I have that year divided by the total registered car within that population. So I have 6.5 million divided by 136. I'll have the probability of getting crash is what? 0.048, right? 0.048. So the probability that anybody getting a crash, right, given that this is the number of cars registered, is 0.048. It's a bit less than 1%.
So are we going all the way to you know how the 8, like we're not just gonna round if it's, you know how 7 is greater than 4?
You can round it up to 9, you can round to 0.5, that's fine.
0.05?
Yeah. That's okay. Does that answer the question here? The reason we don't use theoretical probability, that we don't have the same amount of crash with the number of cars registered. Okay. So the probability of any given car having a car accident anytime is 0.05. Let's go to the next one. Find the probability that when a couple has 3 children, they will have exactly 2 boys.
These are real numbers.
Yeah, those are real data.
Yeah.
All the stuff that in this package I give you is real data. Number 2. So I'll do this in one way, and there's different way of approaching this problem. So if there's 3 children, right, and we're interested in having 2 boys. Okay. So the probability of having 2 boys out of these 3 kids. Now, let's go back to the probability. Let's start with 1 child. Okay? So just think about this problem while I'm doing this. Right? Just try to relate to the 2 problems that I'm doing. So let's go with having 1 child. What is the 2 possible outcomes I can have? Either a boy or a girl, right? That's the only outcome I can have, either a boy or a girl. What is the probability of having either one of them? 1/2, right? I can have a chance 50%, 50%, right? 1/2, 1/2. So this guy goes with the first equation, theoretical probability, where equal chance of those events happening. Unlike the first one, where the amount of crash we have that year and the number of car registered, they're not equal. So we can't approach that method. So we have to use relative frequency. Does that make sense now a little bit? So having 1 boy, I will have either a girl or a boy. And either 50%. Right? Now, we're given 3 children and either having 2 boys. Out of the 3 children, having 2 boys. Then we need to come up with our sample space. Right? Because the equation says the number of outcomes in your sample space, right? So we need to build a sample space that contains this requirement. To do that, there's 2 ways to approach it. Now, if the first one is a boy, then you have a girl, right? If I toss this coin, the first one, does the outcome depend on this one? Whatever that guy is, that does influence it? No, so the same thing here, where the outcome of having boy or a girl doesn't affect the next child, right? So this is child number 1, you can have either one of them. So the next child, you can have either a boy or a girl, right? Think about it. If in the first trial you have a boy, right? Next one you can have either a boy or a girl, because they're independent. Or if you have a girl on the first experiment, then you can have either boy or a girl, right? Is that clear? The outcome of this does not influence what this will do. Okay? So this is our second process, or the second child. So we're going to do one more, because we were asked to do the third one. So I can have a boy or a girl, right? I can have now, think about it, I can have all of them right? I can have either all of my 3 children boys, right? I can have all of them boys, right? So I have boys, boys, boys. I can have 2 boys and 1 girl, right? I can have 2 boys and 1 girl, because we were asked to do 3 children, so 1, 2, 3 children. The next one, I can have a boy, a girl, and a boy, right? That's the combination that I can have. So I have a boy, a girl, a boy. The next one, I can have either a boy, girl, or girl. Boy, girl, or girl. The same, if that happened to be a boy. If it's happened to be a girl, because they're both independent even, they don't influence what the next child will be, right? So you can have either all of them boy or you can have all of them girl. So the next one is having girl, boy, girl. And boy, girl, boy. Girl, girl, boy. Okay. So I can have either all of my children, 3 of my children girl, I can have all my 3 children boy, I can have all this combination here. Okay, this is a possible outcome I can have. If I'm having 3 children and I'm interested to have 2 boys, this is the possible outcomes I can have. Go ahead.
What's the question asking specifically?
2 boys.
So the question is saying if they are trying to have children and want 2 boys and 1 girl,
Yeah.
they don't care about the sex
So
of
that's what we try to approach.
Okay, so they're trying to figure out the likelihood that they will get 2 boys.
2 boys, yes.
Okay.
But we need to have a sample space because we're using this equation, theoretical probability, because each of them have equal chance, right? 50-50. So that's what we try to approach. So the equation said the number of outcome event E, which was two boys, divided by the number of possible outcome of my sample space. So I have to build this sample space. So this is called my sample space.
Yep.
Okay. The possible outcomes. I can have all this variation, right?
I just got confused because when you started around 2 girls and I was going,
No, that's the possible outcome you can have.
yeah.
And it's 3 children. Now the question says, having 2 boys and 2 boys and 3 girls. So look at it here. Let's start with the easiest one. What is the probability of getting all of my girls?
The same is the chance is the same as if you've got all boys.
Absolutely true. And what that be? 1
1
over 8, right? The probability of getting all of this individual to be girl, in my sample space 8, and the only possibility that all of them could be girls is only 1. So it will be 1 over 8 within my sample space. Okay. So I have 1 over 8.
So the 1 over 9.
8. It should be 8.
How do you get 1 over
Because you have in your sample space 1, 2, 3, 4, 5, 6, 7, 8. And the formula says the probability of any event, experiment, that has equal chance or equal likelihood of being having that event is the number of events in your E divided by the number of outcomes in your sample space. This is my possible outcomes in my sample space, right? And if I'm interested in getting all of this individual to be girl, then I have 1 combination of all of the females are girl divided by the total number of my sample space, which is this guy, which is 1 over 8. Okay? Let's go to the next one. All possibility of having boy. 1 over 8 doesn't change. Okay, that's easy. So what's the possibility of getting 2 boys and 1 girl?
2 over 8?
1 over 8.
1 over 8.
But
In that
there's
order,
another
1 over 8.
one, it's just not the same order.
We'll come back to it. 1 over 8.
So are they all gonna be 1 over 8?
All will be 1 over 8. One over 8. A boy, a girl, a boy, you have 1 over 8 chance. All the way down, you have 1 over 8.
Where do you get the 8 from?
The total number of events you have in your sample space, the possible outcomes. Now, we have 1 over 8 all the way down. The question asking us to do 2 boys. What is that, 2 boys?
Yep.
2 boys, 3 girls. I have 1 here. I have 1 here. I have 1 here, right? In different order, but I have 3 different events where I can have 2 boys. Is that right?
We don't want to include the 3 boys because
Well, we'll come back to it. Right? So I have 2 boys here, 2 boys here, 2 boys here, and all boys here. And we said the sum of all this product has to equal to what?
One.
1, right? Has to equal to 1. Now, given that, how many possible do I have to have 2 boys?
Well, in the question it says, they will have exactly 2 boys. So
Exactly 2 boys. Okay.
no, wouldn't 3, the others.
Exactly. Great. Thank you for clarifying that. Exactly 2 boys. And 1 girl. Thank you. So if that's the case, then we have 1, 2, 3, right? So that will be 3 over 2 boys. Will be 3 over 8. If it wasn't what he said, then that would be 4 over 2. Go ahead.
I have a problem with the wording of the question. Because it says that if they're gonna have, that they will have exactly 2 boys, there's no possibility they'll have
Exactly 2 boys and 1 girl.
Well, the question doesn't say the third child's gender or, it just says find the possibility that they will have exactly 2 boys.
Exactly
It
2
doesn't
boys,
know
yeah.
if they're variable.
We're not here wondering about the combination. Are they gonna have the first
No,
2
I-
child that are boy or girl, or are they gonna have 1 girl and 2 boys right after that? We're not here to, we don't care about the order of event, rather within that combination having 2 children, exactly 2.
Yeah, exactly. They're looking to have exactly 2 boys, but it never specifies what the third child will be.
Okay, just think of as a girl. Just
So it has to be a girl. Okay.
1 girl. But if that's, if you go with the first, what you said is, it will be 1 over 2. Let's do a coin. If I toss 1 coin, I have either head or tail, right? Is that clear? And each of them have 1 over 2, 1 over 2, right? Now if I toss 2 coins, I can have, the first one I can have head or tail, right? If my first coin is head, the next coin can be either head or tail, right? The next coin can be either head or tail. What is the probability of getting head or tail? 1 over 2. What's the probability of getting head or tail? The probability does not change for each event, and that'll be 1 over 2, 1 over 2. So what's the possible sample space I can have? I can have either head, head, right? I can have head or tail. Right? I can have tail or head. The last coin I can have either both of them tail. Is that clear? Tossing 2 coins, you can have 4 possible outcomes. If I toss 1 coin, I have either head or I have a tail. Right? That's my possible sample space for 1 coin. If I'm tossing 2 coins, I have a possible outcome of 4 events. Right? Either both coins can have head or tail, or either coin will have head or tail within it. Right? Now, the probability of having both of them are head will be 1 over 2 times 1 over 2, which is 1 over 4, right? Here you can have 1 over 2 probability getting either tail or head for 1 coin, right? When you have 2 coins, your probability of getting those combination will go down. Is that clear? What I'm doing? I'm multiplying 1 over 2 by 1 over 2. Yeah? And I'll do the same thing for tail. Where I can multiply 1 over 2 times 1 over 2, which is 1 over 4. Right? The same here, I have 1 over 2 times 1 over 2, which is 1 over 4. 1 over 4. where I have a sample space, all my possible outcome for a point, 2 point, I can have either head, 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 tail, tail, head, or tail, tail, right? And either one of them have 1/4 probability. The probability of the point will have 1/4, 1/4, right? So this is my sample space for having 2 point, and this is each individual probability. And the sum has to equal to? Has to equal to 1. Okay? So if I increase this to 3 point, if I increase that to 4 point, all I have to do is multiply the bar by each probability. Okay? That's how we determine this to have 8 individuals, or 8 possible outcomes. Right? No? Huh? Okay, let's just the third one. We'll come back to those 2 problems, and we'll stick with those for a while. Let's go number 3.
My problem was I just had a confusion with the wording, I didn't mean that.
Oh no, that's fine. No, glad you asked because I was going to 4/8 anyways, until you mentioned it. So that's okay. So if a single die rolled, find the probability getting 9. So if I toss a single die, I have 6 possible outcomes I can have in here in this dice. If I toss this, and the question says the probability getting 9. Has 9 existed in here? No. So what would be the probability? 0, right? So the probability of having 0 in any dice is 0 because the probability, let's do the sample space. I'll keep doing that. Sample space for dice, and I have 2, 3, 4, 5, 6 possible outcomes. Then 1/6, 1/6, 1/6, 6. And this is the probability of dice. Okay? So the question says the probability of having what? 9 equals, which is the number of possible outcomes in the dice, divided by the total of my sample space, which is, there's no 9 here. There's no 9 here in my sample space, so therefore it's 0 over the number of possible outcomes is 6. That equals 0. Should be straightforward. Now the other question right along with this one says, if a single die rolled, if I toss this die, and what is the probability getting number less than 7? Alright, so the probability less than 7. And I know this is my sample space 1 through 6. And the question says the possibility getting number less than 6. How many numbers are less than 7? 6 of them, right? There are 6 possible outcomes that are less than 7. And what is the total sample space? 6. So therefore, so all the time if I toss this coin, I'm 100% guaranteed to get either any number within my sample space that is less than 7. Right? Is that clear? Number 5. So the 110th Congress in United States have 84 male senators and 16 female. If one of these senators randomly selected, what's the probability that women is selected? Now, the probability of getting female. If this is my sample space, it's called a sample space, male and female, and the probability of senators, probability of either male or female senator will be for male is what? 84. Right, I have 84 out of 100 size of population, 84 are male on the Senate and 16 are female. So therefore, the total of this two is 100 within my population, right? So if I make that population circle, I have 100 seats within the Senate, and out of that, 84 are male and 16 are female, right? This is a large population, and 84 of those are male and 16 are female. So therefore, this will be 84 over my total population, 100. And this will be 16 out of 100.
What did you get the 100?
Well, the sum of the two.
Oh.
The sum of the two is in your experiment, right? Whatever you have in your sample space, the total number of sample space, right? Now, the probability of getting female is in this case 16 over 100. Just like the first form that we have. When it says the number of possible outcomes in your sample space, is how many possible events can you have in your sample space? You have 6 possible, 6 different phases, right? Now let's go back here. I have 84 males. I can't say 2 possible outcomes, even though it's a female and male, but the number of individuals within my population that has 100, 84 of them are guys from different locations or different places, and 16 are female. So the total possible positions that I have is 100. Out of that, 84 is taken by male and 16 is taken by females. Okay? Number 6. In recent year, should be struck by lightning. In recent year, there's 281 of. Can I raise this one? So we have a possible 281 individuals struck by lightning. And the total population of 290,789 population. So our goal is to find the probability of lightning strike that you can have in any given day. Knowing that 281 lightning happen a given year, and then out of the population of 290 million individuals in the country. So this is the same equation as, or the same problem as the first one that we have done, right? Because the amount of individual who struck by lightning is not equal to the number of individuals not struck by lightning. So it's a frequency problem. So therefore, 281 individuals divided by the possible population, or the population of the country, which is 209,0789 million. And that would be 1, 2, 3, 4, 5, 6, 96.
How many zeros?
There are 1, 2, 3, 4, 5, 6. 6, 0, and 96. To round that to 97. Okay. Now, the reason I make this number 6 italic is because we'll do some problem to relate to this question the last problem, which is winning Mega Million, and possibility of finding that you have more chance getting strike by lightning than winning a Mega Million. We'll get to that question. Yes, twice though. Twice. Number 7. This is also another question that has to do with frequency. Right? We are given a frequency for yes or no response. So the question is, the researcher asked 25 individuals, total of 25 possible response that we can have if they like the taste of the new drink. So it's a survey someone performed, and there's 25 individuals he asked, and the question, the response is yes or no and maybe. So there is 15 individuals who said yes, they do like the drink, and there's no, which is 8 individuals that says no, and there is 2 undecided, with a total of 25. Right? So there's a yes or no question, and individual responded this way. It's 15 possible yes, and 8 possible no, and 2 undecided. The question is, find the probability that the person responded yes, no, and maybe, or undecided. So the first thing you wanted to do is, the people that some event, in this case performing this experiment, equals the frequency of that class divided by the total number of individuals that you ask, right? So this will be, for the first one, the probability of yes, for the people who responded yes, right? Then you will have 15 over 25, and the people that replied no, right? For that frequency of the class, which is 8 over 25, right? And the people that said undecided is 2 over 25. So this will be 0.6, that will be 0.32, this is 0.08. And the sum of this has to be, the event has to equal to 1. So if you add this, that should equal to 1. So if this individual wanted to perform the same experiment some other day, he have data that the possibility of individual that he asked, there is 15 individuals that replied yes, they like it. Right? So he can use this data to say, all right, if I go to some other town, the probability of someone replying yes is 60%, or at least 60% of the time. So this is data already he has, or experiment that he performed to determine what the probability of the some outcomes. And using this, he can, or she can project what would be getting yes or no if she performed the same experiment in some other place. That doesn't mean it will be the same all the time, but she has some idea where 60% of the individuals said yes. Right? Also, based on this data that she has, she can decide to continue with her drink, or that drink that she invented. She can continue with this if individuals are satisfied. Right? All right, number 8. Find the complement of each event. So if I roll a dice and get in 4, right? So I'm interested in getting 4. If I toss a dice, which is right here, right? The probability of getting 4 is 1 over 6, and the complement will be not getting what? Everything else, except 4. One, 2, 3, 5, and 6. Right? So that would be number 8. So the complement is not getting those numbers. Selecting a day of a week and getting weekday. The complement will be? What will be for B? Yeah, which will be those, what will be the days?
607?
Think about it, selecting a day of a week and getting a weekday.
207? 207?
Yeah, 2/7, right? So that would be, if you select a weekday, it will be Monday through Friday, you have those possibilities. The complement will be not getting weekend, right? So you'll get it, instead of getting Monday through Friday, you have 2 weekend or weekend days, which is 2/7. Sure. So the complement So the complement will be either Saturday or Sunday. Right? My sample space have Monday through Sunday. If the weekdays are Monday through Friday, the weekend are Saturday, Sunday. If I'm interested looking for one of the weekdays, the complement will be the weekend, which is Saturday and Sunday. Right? Number 9, that will be the last question. If the probability of a person lives in some industrial country is 1/5, number 9, the question says to find the probability a person doesn't live in industrial country. So the probability of the two has to equal to 1, or the sum of the two has to equal to 1, right? The sum of person living in industrial country plus the person not living in industrial country has to equal to 1. So if I'm given the option that a person living in industrial country lives industrial country is 1/5, then the probability not lives in industrial country will be 4/5, because the probability of person lives in the industrial country plus the probability of not live in industrial country has to equal to 1. Same thing saying the probability of event A plus the probability of its complement has to equal to 1. So therefore, if a person lives in industrial country, that is 1/5, plus the probability of not living in that country has to equal to 1. So you subtract, it's 5, right? 1/5. So you subtract 1 from 1/5. So if I do probability of not live equals 1 minus 1/5, which is 4/5. Right? The sum of the two events, the person lives in an industrial country plus not live in industrial country has to equal to 1. If the probability of some event plus the complement has to equal to 1. So therefore, if the person lives, and we know that a person lives in an industrial country is 1/5, so therefore the probability of not living in industrial country has to equal to 4/5 for this equation to work, which equals 1. Okay. If you didn't pass the homework, pass it, please.
Do you want us to make a sign?
I'm sorry. Sorry.
Yeah, okay. Right at the end of the week. I'll just have to sort of go.
Make sure you sign your minutes back. Don't mind the extended, just.
Hey, you guys wanna ride the train?
I'll do it for everybody.
Take a train? No? No, I'm going home today. Where are you at? Oh, you going to Charleston? Well, I'm going home. Where you at?
Yeah, there's like.
My girlfriend. Yeah, I'll just go ride out. We might get stuck in traffic. As long as cigarettes don't bother you. Yeah, you gotta ride.
Yeah.
Oh, dude, I'm sure I heard, but we were off. Yeah, always off there, everyone doesn't know. On your, you want to cancel that? I might never give you the stuff back. I love this thing.
Where do you get it?
From the back.
Yeah, that's true.
Oh,
You
yeah.
said that.
Balance notes from the.
Oh, is it Novus?
Yes, sir. Yes.
I forgot that. It was from the,
Yes, sir.
not from the library, from the first one, where we were buying.
School?
In school, where we were buying
The bookstore.
the books.
Yeah?
That was what I
Oh, I
was.
get some. I like those.
I'm gonna.
Those things are sweet. Yeah, where are you guys at? So you don't mind? Huh? Oh, so you're going all the way back there? Oh, yeah. It's all but that, I'm just gonna go down and get off in the Ponce, you know? That's where I usually go, I walk, I don't know if I can go Star Road that way, you guys know where to go down Star Road to get there? Yeah, I feel like Star Road this time of day would be like, yeah, are you going to the train?
Oh, yep.
Where are you going?
Oh, Sebastian?
Oh, yeah.
Where I get one is this one. One class. This one. I can get it.
So there is no homework due Thursday?
Thursday's exam day.
So there's no homework?
No,
Oh yeah, I forgot my homework, can I just send it to you on email?
bring it next class, please. So you have it after next class.
I can email it to you?
Yeah, you can email it to me, but you can also bring it next class.
I'll do both, just to make
Sure,
sure.
whichever work for you. I'm okay with that.
Did you email that worksheet that you handed out last Thursday to us?
The chapter 4,
The one that you were going over today?
I should,
You did email?
I should.
Okay.
If not, I will upload that again.
Alright.
Some people not getting it.